So pushdown automaton. I said that regular languages can be implemented with just a finite state machine. You don't need any other memory like stack. But sometimes our languages does not cover everything, and so we should enlarge it, we should relax our constraint, and we go to context-free grammar, context-free language, and implement context-free language with push-down automaton. This is the subject of this lecture. So with push-down automaton, it's just a finite state machine, but it has a stack as well. In order that stack represents a kind of memory to know at where we are, to know what has been. Because, for example, because if you want to reverse to learn when something is reversed, then you need to have some kind of memory. So not every context-free language can be recognized by finite automaton. And so what sort of more powerful device could be stored? As I said, we need just a stack. And for example, this is a kind of language that you cannot do it with just finite state automaton. Because, for example, W is just A or B. For example, A and then B, and then you reverse what you have done. So reverse of this becomes AB. So this is part of your language. And you cannot simply do this, implement this with a finite state machine, because you don't know how to memorize this reverse object. So, for example, let's try. For example, we are in state Q0, and we have input A. We go here, we go to state Q1, and then we have input B. We go to another state, for example, and then we have B again. So you see that we don't know how much we are staying at each state. For example, it could be 3B, it could be 4B. We don't know how much, because we should reverse whatever we have done till a particular sequence, till a particular alphabet, and then we should reverse that. And so it's like this. We need something like this, that if A is in the beginning, it should be at the end. If B is in the beginning, it should be on the end, like this, that A is in the beginning, so it should be on the end. So this represents that S that I'm talking about. The same thing for B. B, A, B. So whatever that is in the beginning should be repeated on the end, because we are reversing. Our language is WW the reverse. And so now this one becomes S. So now you understand why this rule that we talk in context-free grammar can implement this language. So we have finite control. So think about it just as a clock. We go from Q3, suddenly you go to another state, which is, for example, Q8, and then suddenly you go to state number 12, or like this. But you also have a stack. So your action not only depends on the value of input tape, but also you need to check your stack, the top of the stack, to know at what value you are. So to take another example, the set of strings of balanced parentheses. For example, we know that we can increment the parentheses, so 2, 3, 4. And when we want to close the parentheses, for example, in semantic parsing, in dependency parsing, you need to know. So we are in state 4. We have counted four times the parentheses. And now, whenever you see a parenthesis like this, you reduce it. So 4 becomes 3, and then 3 becomes 2, and then 2 becomes 1, and then nothing. So you close. So for every open parenthesis, you have a closed one. For open parenthesis, you have a closed one. For open, you have a closed one. So in this sense, the pushdown automaton can implement this. For example, to address this question from yet another point of view, such as rule A, how do we implement A goes to AB? It means that if you are at state A, then reading input A from your tape leads to going to state B. So if you are in state A, for example, if you have input A, we go to state B. Okay, you say, okay, how about this one? How about this one? Because we have 3 things, not 2 things. Then I say, this is the same thing. You are in state A, and you have input tape. It says input is A. You go to state B. But now what? What about B? How do you handle B? Then I say, no problem. I create an object, a data structure like a stack, and put B, this B, little b, on the top of the stack. And so because it is empty, so it becomes this. And the top of the stack is here. So the next time could be, for example, B could be to go to A, for example, C, and D. And so the same thing will happen. Now the top of the stack becomes D. Because your input A, you have an input A, you go to state C, and the top of the stack, it becomes D. So now you will see that even you have 3 things, you can implement it with a stack. And so this is the formal definition. You have a set of states. That is the clock that I was talking about. You go from this state suddenly to this state, and then after some input you go to another state. After some input and some stack go to. But now not only input is affecting your change of states, but also your stack symbols. And your stack symbols does not necessarily have to be one of your input symbols or one of your input symbols. It could be another. But for simplicity in my examples, I use the same thing. I mean, the nature, essence of that is the same thing. And S is initial state. You start from initial state for input A, for example, and stack, for example, B, you go to another state, which is Q3, for example, and then another input stack, you go to some other states. And this is deterministic, but sometimes it is non-deterministic, that I will explain. For example, in neural, if you want to implement it in neural push-down automaton, we say, for example, we create a softmax. Very intelligently, we say, what is the probability that you go to that state? What is the probability that you go to different states? So these becomes these continuous things. For example, the 80% you go to another state, 20% another. So it becomes a trajectory, just like reinforcement learning or control systems. Depending on the input, you have different trajectories. And delta is the transition. So not only you should know what state you are in, but this is, by the way, this is the empty symbol. It means nothing has happened. And so if you are in one of the states in K, and you have some input symbols, and you are the top of the stack or the total stack, it's some states, you have some stack, then you go to another stack, and then you push another elements of this gamma. For example, you're in state S, and suddenly you have input A. Now input A and nothing in the stack. E is empty. I mean, my stack is empty now. Then I go to state S. So I come back here, and I'm state S, and your stack is A. So the top of the stack is A. Another rule that, because these are transition rules, one of these 5 rules, for example, this rule, I want to use that rule. For example, it says that if you are in state S and you receive input B, you go to state S and put it on the top of the stack B. So push B. So you understand how to, and finally you have F. F is your final state. It means that you can accept it if you reach that. So for example, a sequence A, B, B, A is accepted. So it's part of a language. And so, for example, you start from 100 input, you have this input, and then step by step, you change the height of the stack. The height of the stack is, assume that this is the height of the stack. The height of the stack increases, decreases, and suddenly decreases to the last level, to the beginning level of your stack. And so these has very different dynamics. But what is important is, first of all, the height of a stack. So this is another thing, but the height of a stack does not change. For example, if you start from here, we are at the same level of the height of a stack. For example, height of a stack is here. We are at that level. What is important is that whenever you reach final state, it means up to that sequence that you have created, that is enough. That is part of your language and you can accept it. This is another example that you can try. So these are different rules. You, from one state, you have input A from your tape and your stack is empty. You go to state S and push A on the stack. Or the next one, push B on the stack. You go to state S. You begin from state S. You have B as an input tape and your stack is still empty, and this happens. So it's very easy and interesting thing. But these are something that can be generalized to non-deterministic pushdown automaton. And this is interesting because if you watch my playlist for DNA computing, you will see that all of these things are happening inside your body. Your DNA is computing these things to understand, for example, how much protein you should create, or for example, in the field of DNA computing, this is the future of storage. So there is no hard disk like now. So you can store billions of terabytes in your DNA with just some tubes of DNA, and you will see you can implement the DNA for either push down. I can create a machine push down automaton, or a Turing machine. A Turing machine is much more general than that. It doesn't have the restriction of context-free grammar. It's much more general. It's even more general than context-sensitive. So it's like everything could be written, everything could be read. So it's very general, and I've explained an article about neural Turing machine in one of my YouTube videos that you can watch.